Hi guys, today's video is part of Unit 3. Unit 3 is dealing with the gas laws, and Charles' law is actually one of the first gas laws that we'll talk about. It's the relationship of temperature and the volume of gases. So you'll need your notes, pen and paper, your Unit 3 Section 1 packet, and your calculator. So the overview is that we're going to take a look at the relationship between temperature and volume, and so if we change the temperature, what happens to the volume of these gases, and we're going to calculate what those changes are. So the first thing here is I'm going to show you guys pretty much a piston. So on the left-hand side, we have a container. It has a certain volume, and the temperature is T1. If you go to the right-hand side, as we increase the temperature gets higher. The volume also increases. There's still the same number of particles in between the two containers, but the volume will change as the temperature increases. So we know that in Charles' law, at a constant pressure, meaning we're not changing pressure, the pressure doesn't change at all. As the temperature of the gas increases, the volume increases. Conversely, as the temperature of the gas decreases, the volume will decrease. So the temperature needs to be in Kelvin, and we'll discuss why that is. So the temperature and volume are directly proportional to one another. And we'll write out this equation, V1 over T1 is equal to V2 over T2. So that V is volume, and your T is temperature in Kelvin. And we need to make sure that if the volume is in liters, that the volume 1 is in liters, that volume 2 is in liters as well. Same thing with milliliters. As volume 1 is in milliliters, volume 2 should be in milliliters. Temperature should always be in Kelvin. And this is the graph of Charles' law. We have volume on the y-axis and temperature on the x-axis. And as the volume increases, the temperature increases. So when we talk about direct proportions, we want to make sure that we write out that T is proportional to V. So this is actually in your Unit 3 packet, Section 1 packet, and it'll just check the page numbers, and you can always ask me about the page numbers as well. So Happy Birthday balloon is filled with 3 breaths of air and tied so no more air can come in. So it has 3 breaths and nothing else can come in, so we're just going to keep the same number of particles in there. It has initial volume V1 of 400 milliliters and an initial temperature T1 of 285 Kelvin. The air in the balloon is cooled to 265 Kelvin, which is T2, and the volume decreases, which is V2. Third, the balloon is heated to 300 Kelvin, which is T3, and so then we're going to figure out what the volume is. So take a look at the balloons. It's filled with 3 breaths of air, and the volume initially, so this is our V1 at a certain temperature, and this is the initial state. The volume is 400 milliliters, and the temperature is 285 Kelvin. In the second experiment, or with the same balloon, but with a second kind of trial, we've actually decreased the temperature, and then in the third set, we've increased the temperature. So we need to figure out what the proportionality constant is. So pretty much what happens with this little k with each of these measurements. So the first one is showing us V1 over T1. So this is a simple little plug-in. We can put in 400 milliliters, which is our volume, over 285 Kelvin, which is our temperature. And then from there, when you plug this into your calculator, you get 1.40 milliliters, which is right here, over Kelvin. So that's what we'll plug into here, 1.40 milliliters over Kelvin. Let's take a look at the second trial, or after we've decreased the temperature to 265. Notice the K value. There is a typo over here, so instead of 1.4 degrees, it should actually be 1.40. Same thing with K3. The units are still the same, milliliters over Kelvin. In fact, the numbers themselves are the same. So if we have that same balloon, the same amount of gas in there, the proportionality constant should stay the same. So from there, we can figure out what V2 is. So here, they give us K is equal to V2 over T2. We'll rearrange the equation to show that, or to get V2 by itself. So we have V2 is equal to K times T2, and then we'll plug in our values, 1.40 milliliters over Kelvin, and units really matter here in chemistry, so make sure you keep them in there, multiplied by T2, which is 265 Kelvin. Okay. Let's cross out some units. Is there anything in the numerator that's the same in the denominator? If so, we can cross them out. In fact, we have Kelvin here. We can get rid of them, which leaves us with just milliliters, which is good because that's the unit for volume. We always want to double check our units just to make sure that they will cancel out and that we have the proper unit for whatever variable we're trying to find. So punch 1.40 times 265 into your calculator, and we should get 371 milliliters. We want to keep to 3 significant figures, so this K value is 1 to 3 sig figs, and our temperature is 3 sig figs as well, so our final amount should be 3 sig figs. So V2 is 371 milliliters. So let's check to see if this makes sense. We decreased the temperature, so the volume should decrease. And in this case, it has happened. The temperature went down to 265. The volume changed from 400 milliliters to 371 milliliters. So that does make sense. For the third trial, the third part of it, we have to figure out what V3 is. So I'm going to give myself some space. We know that V3, if we rearrange the equation, is K times T3. So let's plug these in. 1.40 milliliters over K times 300. And I'm going to run out of space here, so hopefully you guys can see this. If not, it's multiplied by 300. You can cancel out your Kelvin. And then from there, we'll punch this into our calculator. We should have 3 sig figs at the end. And so we'll have 420 milliliters left. Okay. So let's check to make sure if this makes sense. We can even go from T2. So from T2 to T3, we increase the temperature. So therefore our volume should increase. And in this case, it has. It went from 371 milliliters in V2 to 420 milliliters in V3. We can also double check it with the first set as well. So we're going to go from T1, which is 285 Kelvin. The temperature increased to 300 Kelvin, so our volume should increase as well. In fact, it goes from 400 milliliters to 420 milliliters. And to also keep sig figs, let's make sure that we put a little dot or a decimal. I don't know if mine showed up very well, but this will show that this V3 has 3 sig figs. So we have another balloon, a completely different balloon. This one's a Happy New Year balloon. So we'll make sure that we take a look at all the information, and here the New Year's balloon is inflated with 5 breaths of air. So originally the Happy Birthday balloon had 3 breaths. This one has 5, so it has more air particles in there, or more molecules. It has an initial volume of 600 milliliters at 285 Kelvin. It's heated to a temperature that changes the volume of air in the balloon to 630 milliliters. Next, the air in the balloon is cooled to 265 Kelvin. Calculate the missing values for the New Year's balloon. So, just like in the Happy Birthday balloon, we had a proportionality constant. We have V1 over T1 should give us what the K is. And let's go ahead and plug that in. So we know K is equal to V1, and in this case it's 600 milliliters, over T1, which is 285 Kelvin. And with this V1 for sig figs, just make sure that you have a dot after that 600. Mine isn't showing up very well. Let's see if this one helps. Let's pretend that's our great dot, okay? Same thing there. That shows that 600 is actually 3 significant figures. We'll plug this into our calculators, and we should get 2.11. And let's keep the units. Can we cancel any units? Are there any units that are the same in the top and the bottom? And in this case, there aren't, so we have milliliters over Kelvin. So we'll put that into our value, so 2.11 milliliters over Kelvin. And just like in the Happy Birthday balloon, where all of the K values were the same, from one temperature change to another, same thing here with the Happy New Year balloon. This K will be the same for all 3 of these experiments. So we can go ahead and put those in, and that's supposed to be milliliters over Kelvin, so 2.11 ml over K. So let's plug in what we need to figure out for T2. Let me separate these out. So for the second experiment, we need to figure out what T2 is. So I know I have, let's see, if I isolate T2, I should have T2 is equal to V2 over K. Then let's go ahead and plug everything in. You have 630 milliliters. Again, put a dot right there, just so we show 3 sig figs. It should have been in there to begin with. And over 2.11 milliliters per Kelvin. But if I know I have a fraction over another fraction, this K ends up being on top. Let's check to see if we can cancel any units, and indeed we can go ahead and cancel out the milliliters. So we're left at Kelvin in the top, and that makes sense because we know we have temperature, so we want to make sure that we have Kelvin. So go ahead and plug this into your calculator, 630 divided by 2.11, and we end up getting 299 Kelvin. So let's check to make sure if this makes sense. Our volume initially, the V1, was 600 milliliters. We increased the volume to 630, so that means our temperature should have increased. So T1 was 285 Kelvin, and this is 299 Kelvin. So yep, indeed, they all go ahead and make sense. They all increase proportionally. And let's do the third one. So we're trying to figure out what V3 is. We have T3 and K. Before we even do this, we know that from T1 and T2 to T3 that we decrease the temperature. So if we decrease the temperature, the overall volume should be smaller than both the first two trials. So let's plug this in. If we want to isolate V3 in our equation, we want to get V3 all by itself. So it should be V3 is equal to K times T3. So we know we have 2.11 milliliters over Kelvin times T3, which is 265 Kelvin. Cancel out your kelvins, and you're left with milliliters, which is good because we actually want volume. Plug this into your calculator, and we end up with 559 milliliters. And if you're having trouble with isolating variables, go ahead and talk to your math teachers too. They're there to help you as well. So for 3, we know that we need to use Kelvin, but we have to figure out why we're actually using Kelvin. So we want to prove to you that Kelvin is the temperature scale to use, not Celsius. So that's what we're going to do in number 3. We have the volume of a gas is proportional to its temperature in Kelvin, but not in Celsius. Redo the work for question number 1, so we're going to refer to question number 1, but this time use the equivalent Celsius temperature. So you have your paper in front of you. I can't go back in slides, but at least I can kind of coach you through this. So I'm going to separate all 3 of these. Hopefully I have enough space to put these in. And for T1, I'm going to go back to question 1. And for question 1, my T1 was 285 Kelvin. This time I need to convert it to Celsius. So I know that Kelvin is equal to 273 plus whatever that degrees Celsius is. So when I isolate my variables, Celsius is equal to the Kelvin minus 273. If you forget the 273, you forget the equation, don't forget that this is on table T. So when I plug this in, I know that I have, again, going back from question number 1, T1 was 285 Kelvin, so I'm going to do 285 minus 273, and that means my Celsius is going to be 12 degrees Celsius. All right, so I'll plug that in. Now I want to figure out what my K is. So my K is equal to V1 over T1. I have my V1 and my T1, so K is equal to, and again going back to question number 1, my V1 is 400 milliliters over my T1, which in this case I'm going to try it out in Celsius just to see what happens. So when I plug this in, this should be equal to 33, and I'll put in those values, milliliters over degrees Celsius. So, if this is correct, my K should be the same for each one of these. And so I'll double check. I'll go to T2, and my T2, in my initial question number 1, was 265 Kelvin. So I'm going to use my already rearranged equation. save myself some time. So degrees Celsius is equal to K minus 273. I'm taking the temperature in Kelvin from my T2 up above, which is 265 Kelvin, minus 273, and that's equal to negative 8 degrees Celsius. And I do want to make sure that you keep in mind, this K is not equal to this K. Notice that the K in this one right here, that's Kelvin, that's temperature, versus the K is the proportionality constant. This little K is the proportionality constant, and it's a small or lowercase k. So I'm going to go ahead and plug this in. I'll figure out what my little k is, and I'll use that to help me. So again, if I was able to use Celsius for all of these, my little k should turn out to be the same for each of these. Let's see, I'll go ahead and take 371 milliliters from question number 1. I'll take the negative 8 degrees Celsius from this question. And already I know I have a negative number when I divide this. I end up having negative 46 milliliters per degree Celsius. So already I know that this proportionality constant is not equal to this proportionality constant. And I'll go ahead and do number 3, or T3. My degrees Celsius is equal to K minus 273. My Kelvin temperature in the initial experiment for the third trial was 300 K minus 273. And that gives me 27 degrees Celsius. I'll plug this into little k. So little k is equal to V3, which was 420 milliliters over 27 degrees Celsius. And that ends up giving me 16 milliliters over degrees Celsius. So this is 16 milliliters over degrees Celsius. So let's take a look at all of our k values. If we were able to use Celsius, all of these k values would be the same because it's still the same balloon, but they're not. So this kind of proves to you guys, make sure you switch it over to Kelvin. Don't stick with Celsius. So number 4 on the back has us plot the volume versus temperature in Kelvin for the happy birthday balloon using a straight line, and then plot the New Year's balloon using a dashed line. I know when I read these, I'm not always paying attention, so I'm going to underline the happy birthday balloon with a straight line. And the directions told me to plot the New Year's balloon using a dashed line, so I'm going to underline the New Year's balloon with a dashed line. So go ahead and plot these points for yourself, and you're going to have to switch them back and forth between the sides, but that's going to be okay. Before I have you continue, I do want to make sure that you look at the temperature scales. So the first one on the y-axis, its volume. It goes from 0 to 200. I'm going to put a 100 in between just to remind myself what those little scales are. So every 2 lines is by 100. So I'll put those in. This is really good to make sure that you do this for yourself as well. And then 900. Make sure you do the same for the bottom. Every 2 lines in this case happens to also be 100. It's not always going to be that way. Oopsies, that should be 300. This is 500, 700, and then 900. That should be more on that line. Okay, so go ahead and plot your points. So if you notice all of your lines are your plots are really close to one another, and let's go ahead and connect this with that line that they told us to connect it with. So it's around there. Maybe I can let's see, actually, I might try with a different pen, see how well that works. Use a straight edge too when you're doing this. And go ahead and plot the second part, which is the Happy New Year balloon. So these are our points, and they wanted us to do this with dashed lines. Okay, so as best as you can do it on this graph. Alright, let's go on to the questions. So for 5, use the graphs to find the approximate volume of the happy birthday balloon at 400 Kelvin. And I actually have another graph down here that looks much better than my original one, but use your graph. So they want the happy birthday balloon at 400 Kelvin. So I'm going to go from 400 Kelvin all the way up to the happy birthday balloon, move it on over, and it's approximately 600 milliliters. I'm going to use the approximation sign to make sure that I know that's just an estimate here. For 5b, go ahead and use the graph to find the volume of the New Year's balloon at a temperature of 400 K. So I'm going to go still with 400 K, go all the way up to the New Year's balloon, go across, and this is approximately like 800 and about 850 milliliters. So for number 6, why does the Happy Birthday balloon have a different proportionally constant K than in the New Year's balloon? So we have to think about what the major difference was between the two balloons. So go back and read the problem if you need to. And if you noticed, the Happy Birthday balloon actually only had 3 breaths in it, and the New Year's balloon had 5 breaths. So each of these had a different initial volume of the of air in each of them. So they each had a different initial, not only volume, but an initial number of particles. Okay. All right, number 7, the beginning volume of gas is 500 milliliters at 20 degrees Celsius. The temperature is raised to 35 degrees Celsius. What's the new volume of the gas? So we have a lot of word problems in here. Don't be scared of them. They only have a few variables in here. So I know that we have 500 milliliters at 20 degrees Celsius. So milliliters is a unit for volume. I'm going to make that V1. It's at 20 degrees Celsius, and that's temperature, so that's going to be T1. Then the conditions change. The temperature is raised to 35 degrees Celsius. So this is my T2. What is the new volume? So I know volume is V. That's going to be the new volume of the gas. So whenever you're doing word problems, or any of these problems for me, you're going to write out what all of your variables are. So V1 in here, T1, V2, then T2. Get used to this, because you're going to be doing this a lot. So your V1 is 500 milliliters. Your T1 is 20 degrees Celsius, but don't forget, we need to convert this over to Kelvin. So you can actually just add 273 to this. This is 293 Kelvin. And that's because Kelvin is equal to your 273 plus whatever your degrees Celsius is. So your 273 plus 20, in this case, gave me 293. Your V2 is your unknown, that's your X. So I'm going to make sure it's still in the same unit as my initial volume. So that's going to be in milliliters. And then your T2, that is your, let's see, that's 35 degrees Celsius. So add 273 to it. We should get 308. And then from now, we want to make sure that I know what that equation is. So I remember that from the beginning, we have V1 over T1 is equal to what V2 over T2 is. I need to solve for one of the variables. So I need to solve for V2. So I need to isolate V2. So that means that my T2 gets moved up. So V2 is equal to V1 times T2 over T1. My first volume was 500 milliliters. And I'm going to keep my units in here because units, again, are super important here in chem. 293 Kelvin. And my T1 is 308 Kelvin. And I'm going to see if I can cancel out any units. So are there any units here that are the same on the top and the bottom? In this case, it is Kelvin. I'm going to get rid of them. And that's good because I want volume, and milliliters is what's left over. So plug this into your calculator. I want 3 significant figures at the end. So my calculator says 525.597, etc., etc. So I want to go from the left to the right and count 3 sig figs. So I have 1, 2, 3. So then I'm going to look at my fourth one to see if that increases my third one. We're going to see if that rounds. And in this case, it does. So it ends up being 526 milliliters. I'm going to put a box around it so that way I know that that's my final answer. So let's figure out if this makes sense. My temperature had increased, so we want to make sure my volume has increased. In this case, it has. It went from 500 mils to 526 mils. So let's show you what you will get points for. You'll get points for making sure that you have all of these written out. You'll get points for at least your rearranged equation, your proper rearranged equation, your plugged in values, and then you'll also get credit for your final answer being correct with sig figs, units, and the box. Okay, so make sure that you have all four of them. So you have the correct answer, sig figs, units, and the box. All right, and let's go to number 8. Suppose you have a Valentine's Day balloon with a volume of 300 milliliters at 300 Kelvin. Calculate the proportionality constant for the Valentine's Day balloon. Is it larger or smaller than that of the birthday balloon? So let's go through. I know 300 mils at 300 K. So my volume is 300 milliliters. My Kelvin is my temperature is 300 Kelvin. And my proportionality constant was K is equal to V1 over T1. So let's plug these in. Let's double check. My temperature is in Kelvin. That's good. So my K is V1 over T1. We have 300 milliliters over 300 Kelvin. Don't even need to plug this into your calculator, guys. This ends up being 1 milliliter over Kelvin. So is this a larger or smaller than that of the birthday balloon? So check the proportionality constant for all of the other two balloons, and you'll find that this Valentine's Day balloon actually has a smaller constant. All right. At the same temperature, we'll go ahead. So the Valentine's Day balloon has a smaller K than, and I can't fit this in, but hopefully you guys can, than the birthday balloon and the New Year's balloon. Also box that response in so that I know as your grader that that's what your answer is. So for B, at the same temperature, which balloon is smaller, the Valentine's Day balloon or the New Year's balloon? So we have to go back through and figure out, okay, what was the volume of each of them and what would end up happening? So in this case, the Valentine's Day balloon ends up being your smaller one. Let's go through. On the next page, there's a set of questions for you. And this is just, again, coaching you how to answer those questions. So a gas occupies 12.3 liters at a temperature of 40.0 degrees Celsius. What is the volume? So what is the volume when the temperature is increased to 60.0 degrees Celsius? For this first one, I went ahead and put the V1, T1, V2, T2 lines for you, just to remind you. You will still need to put these lines in for all of the other ones as well. So my V1, I'm looking for anything in liters or milliliters. That's 12.3. My T1 was originally 40.0 degrees Celsius, but I know that needs to go into Kelvin, so that ends up being 313 Kelvin. My V2 is my unknown. I have no idea what that is, so I'm going to make it X liters because my V1 was in liters. And my T2 was 60.0 degrees Celsius, which is 333 Kelvin. Alright, so let's make sure we put in our equation. V1 over T1 is equal to V2 over T2. We don't know what V2 is, so we're going to isolate V2. So V2 is equal to V1 times T2 over T1. Let's plug in our values. So we have 12.3 liters times T2, which is 333 Kelvin, all over T1, which is 313 Kelvin. Let's cancel out any units. In this case, I can cancel out Kelvin. That's good because I want liters at the end for my volume. And plug this into your calculator. We end up having a lot of digits in there. Okay, it's not a big number. This is when people are saying, oh, I have a big number in here. It's not really a big number. It's just a lot of digits in there. So my first, I need to check to see how many sig figs everything had. All right, so V1 had 3 sig figs, T1 had 3, T2 had 3, so my final answer will be in 3 sig figs. So go 1, 2, 3. See if my fourth one will make my third one bigger, and it does. So this ends up being 13.1, and I want liters at the end. So 13.1 liters. Again, you get points for having your plugged in values correctly, your rearranged equation, your plugged in equations, and then you get points for having your proper answer, so your correct answer, in correct sig figs, with correct units, and a box. Okay, so don't miss out on any of these points, okay? Alright, so the summary, Charles' law, temperature in Kelvin, make sure it's in Kelvin, and volume are directly proportional, so your V1 over T1 is equal to V2 over T2, and the graph below shows what the diagram below shows what the graph would look like when volume is in the y-axis and temperatures in the x-axis. And it's a very linear relationship that's directly proportional. So let me know if you guys have any questions. I'm sorry this was a long video, but it went through a lot of the math for you. Take care and have a good day.